All right. So we're going to start question number 5 here. And so we're going to start by eliminating the constant 3 and say that this series behaves like a series of 1 over 2n. We remove the non-dominating term now. And so we have the series here an, and we have the bn now. All right. So by the limit comparison test, we're going to have to look at the limit of the ratio an to bn. What that's going to be is 1 over 2n plus 3 over 1 over 2n. Here is where we'll do some algebra. Meaning, we get the limit now, 1 over 2n plus 3 times 2n over 1, which gives us the limit of 2n over 2n plus 3 as n goes to infinity now. Okay. We could use calculus 1 or calculus 2. So by now we've been using calculus 1 for the most part, meaning divide by. We can divide by the variable to the highest power in the denominator. So let me do this again here. Meaning we can divide by 2n. That's not an issue, but I'm going to try to be consistent here. N, and n. So that this limit now is 2 over 2 plus 3 over n. So this is as n goes to infinity. So by properties of our limits now, we get 2 over 2 plus 3, limit n goes to infinity, 1 over n. And now this limit is 0. So we get 2 over 2 plus 3 times 0, or simply 2 over 2 equals to 1. All right. Here's the constant. Here's that c, and that c is in fact positive. So what that means now is by the limit comparison test, either both of these series converge or they diverge. So let's take a closer look at this behaves like series to determine whether this series actually converges or diverges. Now, I'm going to pull out the 1/2 constant by properties of series here. You got 1 over n, and we know this particular series diverges. This is the divergent harmonic series, the very famous harmonic series. So 1/2 times infinity is infinity. So that means both of the series diverge. So we're going to say this equals infinity, which means diverges. I want to say it diverges by the limit comparison test now. So this is how we look at this particular problem, number 5. Okay. Number 6. We're going to remove the non-dominating terms from both the numerator and the denominator here. 4 to the n and 6 to the n really dominate this series more than just the variable n. So this series behaves like a series from 1 to infinity, 4 to the n over 6 to the n. Okay. Now, just doing a little algebra on this. Properties of exponents. This is going to be 4/6 to the n. Okay. We have an here. And over here, is going to be the bn. So we'll look at the limit now of the ratio an to bn, which is the limit of n plus 4 to the n over n plus 6 to the n. And I guess let's divide by 4 to the n over 6 to the n. So we're going to do some algebra over here. And what that means is we take the limit now of n plus 4 to the n over n plus 6 to the n times now 6 to the n over 4 to the n here. Okay. So we get the limit now by distributing n plus, well, let's make sure, n times 6 to the n plus 4 to the n times 6 to the n over n times 4 to the n plus another 4 to the n times 6 to the n. You got to look at this limit. But before we do that, let's simplify using some algebra, meaning this is 24 to the n. 24 to the n. So we have the limit, n goes to infinity, n times 6 to the n plus 24 to the n over n times 4 to the n plus 24 to the n. That's a little funny there. Okay. Now, what we're going to do again is essentially a calculus 1 move. Even though we say we divide by the variable with the highest power in the denominator, this isn't really the case here because you're not looking at polynomials. But we're going to divide by every term by that 24 to the nth power here. Okay. 6 to the n divided by 24 to the n. Let me put that in red. Plus 24 to the n over 24 to the n times 4 to the n divided by that 24 to the n plus 24 to the n divided by 24 to the n. So let's see what we get when we simplify here. The limit n goes to infinity, we get n over 4 to the n plus 1 now over n over 6 to the n plus 1. Okay. Now, by properties of limits, what you're going to end up getting is the following. So let me get this here for you guys so you can see what's going on. Properties of limits. Limit of n over 4 to the n plus the limit of 1 over that limit of n over 6 to the n plus the limit of 1. This is as n goes to infinity. Essentially, we want to know what both of these particular limits go to, is what's happening here. All right. So I want to note here that we're going to look at the limit now as n goes to infinity, n over 4 to the n. So what we know here is we're going to get infinity over infinity, an indeterminate quotient here. All right. So we're going to have to apply now L'Hopital's rule. So by L'Hopital's rule, we know we got to take the derivative now. And let me do this here. I'm going to have to change the variable to x. So I'm going to change the color because in order to apply L'Hopital's rule, this is defined over a real variable x, not having the domain being natural numbers. All right. So we're going to have to differentiate both the numerator and the denominator. Now, if you guys recall here from Calculus 2, now using L'Hopital's rule, this will be the limit as x goes to infinity of 1 over the derivative of 4 to the x power, which will be 4 to the x natural log of 4. So this means that the limit's now going to be, since the variable here is going to infinity, natural log 4 is a constant, this limit equals 0. So that's saying that the limit now here is also 0. So we have this limit being 0, this limit being 0, and we get 0 plus 1 over 0 plus 1, 1 over 1. The limit again is 1. There's your c, and c is a positive number. So what this is saying here, that both of these series converge or diverge. Now, let's take a closer look at what this series actually is. Okay, because we actually notated that this is 4 over 6 to the nth power, which is actually 2/3 to the nth power from 1 to infinity, 1 to infinity. We're out of space here. But I want you to notice that what you're looking at is a convergent geometric series. And that's because your R will be 2/3, and the absolute value of R, which is the absolute value of 2/3, is less than, which equals 2/3, which is less than 1. So that means this original series in number 6 also converges, we'll say, is less than infinity. The series converges by the limit comparison test. All right, number 6. Number 7 now. All right, number 7 here. Let's take a look here. Okay. There we go. Weird. This here is our AN. We're going to remove the constants now, so that this series behaves like a series that goes from 1 to infinity, n over n cubed, by removing those two constants. What that means, by using some algebra, that the series is 1 over n squared. All right. So that we can actually use either. Well, I'm going to use the original here, AN. It might make our algebra easier. Not sure. This is your b to the n. So we need to look at the limit now of the ratio AN to BN, which is a limit of n plus 2 over, let's see what's there, n plus 1 cube divided by n over n cube here. We're going to have to do some algebra now. So this is going to be the limit now, n plus 2 over n plus 1 cube times n cubed over n. The limit, n plus 2 times n cubed over n plus 1 cube times n. So if we do just some simplification here of some algebra, I guess we were going to get this squared term. We get the limit now of n squared n plus 2 over n plus 1 cubed now. So one thing we can do is just simply multiply. There's a few things. Well, we can distribute, I guess, and then expand the the cube there. We'll get n cubed plus 2n squared over n plus 1, n plus 1, n plus 1. Just doing a little bit of algebra. So the algebra down here should give you n squared plus 2n plus 1, but we have to multiply that by n plus 1. So we get n cubed plus 2n squared plus n squared plus 2n plus 1, which gives you n cubed plus 3n squared plus 3n plus 1 by expanding the n plus 1 cube here using algebra. All right. We need the limit here. Use calculus 1. Divide every term by the variable with the highest power in the denominator, which you end up getting is the limit now of 1 plus 2 over n over 1 plus 3 over n plus 3 over n squared plus 1 over n cubed. So, ladies and gentlemen, when we apply the limit as n goes to infinity, this term will go to 0. This term goes to 0, goes to 0, goes to 0. We're left really with 1 plus 0 over 1 plus 3 zeros, and this is 1 over 1, and that equals 1. Greater than C. It's positive. Is that C value? It's positive. So we got to remember that both of these series will converge or diverge, because this particular series, the Bn series here, is a convergent P series where P equals 2. It's convergent P series. What that means is this particular series is also convergent. So we have convergence by the limit comparison test. Number 7. All right. Number 8. Alrighty. So for this particular series, this will be my AN. However, we're going to remove the non-dominating terms here. Well, the constant and the n's. We're just going to work with the n squared over n cubed. So this particular series behaves like 1 to infinity n squared over n cubed, which is really going to be 1 over n. So an now again in blue and bn over here. All right. The limit of the ratio an to bn is that limit of n squared minus 5n over n cubed plus n plus 1 divided by 1 over n. You're going to use algebra here. Every time I get that purple highlighter out, you guys know we use algebra. The limit n squared minus 5n over n cubed plus n plus 1, that's going to be times n over 1. Which means now we get the limit of n cubed minus 5n squared over really just n cubed plus n plus 1, because we're distributing here and to the numerator. So yet again, you get a Calculus 1 question where we divide every term by the variable with the highest power in the denominator now. Yet again, so we get the limit now 1 minus 5 over n, 1 plus 1 over n squared plus 1 over n cubed. All right, this is as n goes to infinity. So now, as you take those limits, this goes to 0, goes to 0, goes to 0. You are left again, really eventually with 1 over 1, where this limit is 1, it's positive. This is greater than 0. This is that C value. It's finite and positive. So what that means is both the series will converge or diverge. Now, what we know is that this is the very famous divergent harmonic series. It's a harmonic series, and that series diverges, equals infinity. What that means is this series also equals infinity. Diverges by the limit comparison test. Okay? They both diverge by the limit comparison test. All right. Number 9. Here's R, AN. What we're going to do here is remove the constant, and this series behaves like one over n square root of n squared, which simplifies to not 1 but 2, 1 over n times n, or we can simply say 1 over n squared. So this is going to be our Bn. All right. We're going to have to look at the limit now of AN over BN, which is the limit of, I might need more space, one over n square root of n squared minus 1 over 1 over n squared here. We're going to use some algebra here. limit 1 over n, square root of n squared minus 1 times n squared, which is going to be the limit now of really n over the square root of n squared minus 1 here. Okay. Okay. We're going to have to apply the limit. And a couple of things to observe. This will give you infinity over infinity. And you could try to use Calculus 2 and L'Hopital's rule. But I'm going to do sort of this dividing both terms by the variable to the highest power in the denominator. Now, believe it or not, you look at this and you say, well, it must be n squared. And the answer is no. You're going to divide by n. And you say, why? Because you really have the square root of n squared there, ladies and gentlemen, which is n. Now, I can write this a few ways here. I'm going to say this. N is the square root of n squared here. So, the limit now, as n goes to infinity, the numerator is 1. The denominator is n squared minus 1 divided by the square root of n squared. So when we start to use the algebra in the denominator now, that's the square root of n squared minus 1 over n squared by properties of radicals, which gives us n squared over n squared minus 1 over n squared. In the denominator, I got 1 over, well, the square root of 1 minus 1 over n squared is what I have. So take a look at this. This is using algebra. That's the limit. N goes to infinity. 1 over square root 1 minus 1 over n squared. Now, by properties of limits, I get 1 over square root of 1 minus the limit. N goes to infinity. 1 over n squared. Now, this goes to 0, which means you have 1 over the square root of 1 minus 0, 1 over the square root of 1, 1 over 1. This limit equals 1, which is a positive number now. All right. So what that means is by the limit comparison test, both of these series either converge or they diverge. Now, this series is a convergent P series. What is P here? P is 2. It's a convergent P series. So what this means is both the series converge. So this is convergence. And we're going to end up saying we converge by the limit comparison test. Convergence. Both series converge. All right. Number 10 now. Just going to check something here online. All right. Now, I'm going to take a look at this particular series here. This series doesn't have any dominating terms to remove. So, ladies and gentlemen, I do not believe this is part of the limit comparison test questions. So we're going to have to get back to this one, but I don't think that's part of limit comparison. So I'm going to double check my notes and where we got this question, but I don't think limit comparison test is going to apply here. There's going to be another test that we use. But anyway, I hope you guys enjoyed the demonstration.